Hello students, welcome back to the online interactive class on strength of materials. Today we're going to learn some of the important aspects of elastic behavior and plastic behavior and some elastic limit on this today's class. So the class is divided into three parts. Okay, so in the beginning we'll have a quick review on our previous class. Then we're going to have a discussion on some of the topics like elasticity, plasticity, and elastic limit. Then we'll turn on to the dealing with some simple problems. Okay, so in the previous class, let's have a quick review. In the previous class, we had an important discussion on concept of stress. So this is nothing but we have discussed earlier. Okay, when a body is subjected to any kinds of external agencies, this is said is an axis. Okay, so when a body is subjected to any kinds of external agencies like forces, so it offers an internal resistance within this material of the body. So due to the coercive forces which are present in between the molecules. Okay, so this offers a resistance to the action of these external loads. So this induced resistance are developed reactive forces against this applied loads. We call it as the stresses. Okay, in the going to the point of strength. Okay, so when a body is loaded by means of some loads or external agencies, so it undergoes the deformation or it undergoes the change in size and shape in its dimensionality. Okay, so due to this an action, so it undergoes and change in size and shape along the direction of the load. Okay, so the ratio of this change in shape during its loading condition to its original shape before it was loaded will give you the rate of strain or value of strain it is occurred inside the body due to the action of external loads. Then we moved on to the next topic of classification of stresses. Okay, so based on the type of forces acting on different types of material, these stresses are classified into direct stresses and indirect stresses. So coming to the direct stresses, what is meant by the direct stresses is nothing but just take one simple bar, okay, and assume this is the axis of the bar. So if any loads which are acting in line with this axis of the bar are parallel to the axis of the member, okay, and its direction is maybe the away or towards the body, it depends the type of the force. So when a external agency is acting in line with the axis of the members or parallel to the axis of the member, then the types of stresses induced to these kind of loading conditions is called direct stresses. The stresses are directly induced in the material. So due to the action of tensile force, there will be a tensile stress induced in the body, or due to the action of compressive force, there will be a compressive stresses. There will, if the action of force is shear stress, shear force, the stresses induced is shear stresses. Okay. In the similar way, when we some of the examples for this direct stresses we have seen the tensile. So if the direction of this external force is away from the body, then we'll term this as tensile stress. If the direction of this force is acting towards the body, we'll term as compressive forces. Then we have another type of stress called shear stress. So these are the three different types of stresses will come across the direct stresses we are going to discuss in our particular unit. Then we have seen what are the types of indirect stresses induced in a material. So these are the stresses induced in a materials when the action of the forces not in line with the or not in parallel to the axis of the member. For example, take out this condition, say bar, and imagine this is an axis of the bar. So take a load member or an external agency of magnitude P. So this is the line of action, vertical line, and this is the direction downwards, okay, acting on the member. So in this case, the line of action of the force is in perpendicular to the axis of the member, okay. Take another condition like, so a bar is subjected to a twisting like this, right? So due to the action of equal and opposite couple, so these two conditions, here the loads are external agencies are not acting parallel to the axis. The stresses induced due to these condition of loads are the types of stresses induced to these kind of forces are called as indirect type of stresses. So we can observe the type of stress induced due to this lateral direction of force. We'll call it as this lateral direction or transverse direction of force acting. So in this case, we can see the bending stresses, and then in this case, we see the torsional type of stresses. They form the basic examples for indirect stresses. And next, we moved on to the topic like discussion on direct stresses, particularly in the unit 1. So direct stresses, what are meant by the direct stresses? Individually, one by one, like what is the tensile stress, what is compressive stress, and then what is shear stress. Let's take one tensile stress, okay. What is mean by this tensile stress? We'll have a quick review on this. So let's take one bar element for this also, one bar member. So before this, I'm going to have one simple demonstration or one particular member is there here. So take a look out at this particular member. So this member is spring. So look out my hands. My hand is trying to tense this away from this load, or my hand is moving out from this member particularly. So by looking at the direction of my hand, when the forces acting in line and away from the body these are the types of loads or forces which are in contact with the body and they are moving away from the body, are called as tensile forces, or we'll call it as pull type of loads or tensile loads or forces. Okay. The material of this member, this spring, the material of this member opposes this kind of action due to the action of tensile loads. Okay. So this develops an resistance due to the presence of this coercive forces. Right? So we have seen this in the concept of stress. There will be a induced resistance against to these kind of types of loads. So the stresses induced to these kind of tensile loads is called tensile stresses. Very simple. In a simple word, the resistance obtained by the body against the action of tensile loads is called tensile stresses. The nature of this tensile stress, it tends to increase the length of a body or increase the geometrical length of a member. Okay. So this is an example of one direct stress because its line of action is in line with the axis of the member. Okay. So the sign convention for this tensile will take it as positive in generally. Okay. So next we'll go to the another type of direct stress called compressive stress. Okay. Here the direction of force acting is towards the body. Take the same spring member here. Both the hands are trying to pull this member in this direction. By looking at my hand direction, the loads are acting towards the body. They are acting towards the member. Okay. The resistance developed in the member against these kind of loading conditions are called as compressive stresses. So with an illustration of this simple bar sketch, okay, So take out this an axis of the bar. So the loads are acting in line with the axis of the bar, right, on either side, and they are the direction of the force is towards the body or towards the member of magnitude P. Okay. So due to this also the body or member develops an internal resistance, right? So against this force there will be an internal resistance. So the stresses or resistance developed to these kind of compressive loads are called as compressive stresses. And then the nature of this compressive stress is to decrease the length or geometric length of the bar. It will tries to shrink the body or push the body, okay, towards its acting direction. Then we can observe here in both the cases the corresponding strains are. So in the case of tensile stress, it undergoes change in length, right? It undergoes the change in length by extending its length. We'll call it as delta L, right? So when we take out this length of the bar is original length before it was loaded, and this is the final length after it was getting extended due to the action of loads. So coming to the strain or tensile strain, so this is a change of length due to the action of external load to the original length before it was loaded. So here the change in length is, so first the final length due to the action of external load minus the original length divided by the original length. So that will give you the extension it has occurred due to the action of these tensile loads. So this ratio will give you the tensile strain epsilon T due to the action of corresponding tensile stresses. Similar way, when we take out the compressive strain in this case, so due to action of this compressive loads, so the body is going to shorten its in length or it gets compressive or it gets squeezed, okay? Length becomes shorter. So this is the change of length we have occurred. So if take this is the original length before it was loaded, right? And this is the final length after loading, okay? The corresponding compressive strain will be given by the change in length to its original length. So here, the change in length is given by original length minus how much length it is compressed due to the action of these push type of loads divided by its original length. So this ratio will give you the corresponding compressive strain. So you can look out that some of the images we have seen, slides images, okay. Here we can see, so at this particular due to the action of this tensile load which is moving away from this particular rod, it tends to increase this length by means of delta L. Okay, so this change, this original length of the member and then extension, the ratio of this change in length due to action of this force F to its original length will give you the induced corresponding tensile strain. Similar way, when you look at the compressive stresses, see a body is subjected to compressive force which is acting towards the member and it's try to squeeze the member or shorten its length. So these are the effects of tensile and compressive forces, and related tensile and compressive stresses are induced in a members. So next we moved on to the another important type of stress, direct stress, called shear stress. So these are the types of stresses. Third one, third example of direct stress is shear stress. So take one simple block for explanation of this concept with this illustration. Okay, so this is A, B, C, D, as we have done in previous class. See, if we made an axis here at this particular section, XX, okay, and the top surface of the block is subjected to one tangential force. To keep in equilibrium, the bottom surface is subjected to an equal resistance. Okay. Here, if we take one part, our upper part, we'll call it this is G and this is H. Okay. So if you write this in particular sections, so due to the action of this tangential force, the material of this particular part will offer say resistance against this applied tangential force. So this shear stress is usually induced in sliding members or rubbing members. Okay. So when the tangential force applied on parallel to the surface of the members, the stresses or reactive forces developed in the member, such type of stresses are called as shear stresses. Nothing but the shear stresses is so shear resistance developed are offered by this particular area. Okay, so that is shear area. So when we look at this with this illustration, see, this is the initial position of the block. So after it is subjected to tensile force, it will undergoes a deformation in its applied direction. Okay, so when we take out this displacement or deformation along this applied direction to this vertical height will give you the corresponding shear strain induced due to action of shear stresses. That is, the corresponding shear strain equal to the displacement occurred in this direction. Okay, that is, we'll call it as in transverse direction. So displacement in transverse direction to its vertical height or distance from its bottom surface will give you the rate of shear strain induced in a material. Okay, so these are the basic three different types of stresses we have discussed in the previous class, and later, as I said, the indirect stresses. Okay, so we have an example this. So the stresses induced due to by any moments or due to any twisting actions, such type of stresses are called indirect stresses. The examples, as I said in the beginning, the bending stress or torsional stress forms the two basic examples, as we have seen in the animations. Okay. So next we'll move on to the Hooke's law. What is Hooke's law? As I said in the starting of the class, so Robert Hooke is an English mathematician. He conducted this law. So this law states that stress is proportional to the strain up to some certain limit called elastic limit. Okay. So we know that whenever a body or member subjected to external loadings, it undergoes certain deformation. Okay. So whenever this deformation is directly proportional to the induced stress in a member up to the elastic limit. That means to say, stress sigma is directly proportional to strain. So when the stress induces due to the action of more load, the rate of strain induced or the rate of strain occurred is also increases. So then the ratio of stress by strain will give you the equal to one constant called proportionality constant. So are also called as moduli of material. So this moduli of material is different for different materials and different types of stresses. Okay. So we'll see that in the later one. Okay. So now we'll have one simple experimental demonstration. You're going to understand what is meant by this Hooke's law. Look at this physical experiment setup. Here we have So one member or one force is acting on a spring member. See, you can the magnitude of force is acting. So from 0.5 Newton, 0.9 Newton. So similar way, we are observing a linear displacement. So along its force action direction. That is for 2.4 Newton, we are getting 0.004 meters of displacement. 3.7, we are getting 0.006 meters of displacement. When we keep on acting, we are raising the load or force on the spring member up to 14.5, it attains 0.022 meters of displacement. We plot this spring force and displacement in terms of a graph. See, it obtains a linear relationship. So you can see it here. So up to some particular limit, the rate of stress induced or the rate of deformation occurred will be having a proportional to each other. Whenever the stress increases, the rate of strain also increases. If the induced value of stress decreases, the deformation or rate of strain is also becomes less. Okay, so this holds good up to some limit called proportionality limit. So thereby we use this principle of Hooke's law in up to it holds good up to the proportionality limit. That's why we can apply this Hooke's law principle in linear analysis of designs or stresses, and designed by working stress methods, we can have a significant role. So next we'll see what is elastic constant. We have three different types of elastic constants. Okay, we're going to see on this one. So as I said in the beginning, okay, and importantly, the concept of understanding the direct stresses is very important, because we are going to deal the problems on direct stresses or aspects of direct stresses in this particular unit. So I hope it's clear now, all of you, what is meant by the tensile stress and what is meant by the compressive stress. So what is the force acting direction in tensile, compressive and shear stresses, okay, and corresponding rate of strains or corresponding tensile strain, compressive strain and shear strains induced in a materials. Okay, from the Hooke's law, so it is concluded that the ratio of shear stress to corresponding strain is constant up to some limit called proportionality limit. So in case of it is direct stresses or normal stresses, whether it is a tensile or a compressive, we'll call it as a modulus of elasticity. The constant, proportionality constant, is termed as modulus of elasticity or Young's modulus. So it is denoted by the letter E here. So the ratio of stress to strain is equal to constant. In case of direct stresses, it is the moduli of material is termed as elastic constant. It is expressed in usually Newton per meter square. So in case of shear stresses, the ratio of shear stress to corresponding shear strain is equal to a constant value. That constant is termed as modulus of rigidity or shear moduli. It is denoted by the letter G. In sometimes C also we can represent the shear modulus. So in case of volumetric distortion due to the action of direct stresses, so on the members, the ratio of this direct stress to the corresponding volumetric strain is equal to one constant, and this constant is termed as the bulk modulus. So these three, the modulus of elasticity are Young's modulus and shear modulus, and bulk modulus will form the three elastic constants of a materials. So this helps in understanding the elastic behavior of materials under the conditions of loading. Next, we'll move on to today's topics like elasticity. Okay, so first we'll see what is meant by the elasticity. Okay, so we know that every material will undergoes deformation, or it will undergo some change in size or shape in its dimensions due to the action of external loads. So whenever we remove the external loads from that bodies or members, so it will regains back. It will regains back its original size and shape after the removal of that external loads. So this kind of nature of a material is called elasticity of a material. So, so this elasticity will be applicable up to some certain limit. So within that particular limit, okay, the members or bodies will come back to its original size and shape in its dimension after removal of the external loads. In a simple words, it is a mechanical property. It is an important mechanical property of materials by virtue of which regains its original size and shape without any fracture or without failure after removal of external loads. So you can see there's some animation here. So it is compressed due to external force or by means of anything. After removal of, it will regaining back its to original position. See here, in this case also, the rubber is expanded. So after removal of the expansion, it will coming back to its original position or size and shape. So usually all the materials will possess some elasticity up to some limit, including glass also. Okay, it is an important property or in finding the strength of different materials. Usually elastomers and some of the polymers like natural or synthetic rubbers will be having a more elastic in nature. So coming to that elastic limit, what is meant by elastic limit? Just now we have discussed that. Okay, so the material whenever it is undergoes or subjected to loading, it will undergoes the deformation. So after removal of the particular load, it will come back to its original position. So this kind or this nature is limited to some certain limit or some particular value. So beyond that value or beyond that limit, if we further increase the load or if we further increase the rate of stress induced, then the deformation occurred due to that value of stress will not be coming back to its original size and shape. It retains, it goes to the plastic state or it retains its deformation permanently. So this limit, the maximum limit up to which the material regains its original size and shape after the removal of load is called as elastic limit. So elastic limit will be differ for different materials and different types of stresses. Okay. So next we'll go to the plasticity, another important property of a member or materials. You can see this. We know that. So when a member is subjected to loading, so it will occur the deformation. This deformation or induced stresses completely vanished after removal of the load within that elastic limit. When we further increasing the loading condition of a member, so it induces more stresses in the body that leads to occur more rate of strain in the member. So beyond that particular elastic limit, so the material sets to a one permanent deformation. That means, so even after the removal of the load also, it will not come back to its original position. See in the cases here, the first, the bar rests by two pins, okay. So it is loaded by some vertical downward force in the figure 1. So in the figure 2, it is undergone some deformation. Some deformation is occurred. The third case, you can see that there is some permanent set, there is some residual strain completely set retained in the member even after the load is removed. So this state of or this nature of a materials is called as plasticity or plastic nature of materials. Okay, so that is, it is also one of the important property in finding in determining the strength of materials, by virtue of which it will undergoes a permanent deformation without fracture even after the removal of external load. That means even we remove the external loads from the body also, it doesn't regain its original size and shape. So some of the examples for this plastic materials are you can take rocks, soil, and cements are the will form the basic we come across in our daily life as a examples for plastic materials. So these two properties like elasticity and plasticity and elastic limits will play a prime role in determining the strength of any materials we use it in our various structures. Okay, so next we'll move on to the some important dealing with some basic problems related to the direct stresses. Okay, so before we going to that, just take an important expressions what we have come across in this particular topics of direct stresses. So before we deal with the problems, okay, so it is better to remember some of the mathematical expressions which we use it in solving the problems. Okay, so while solving the problems, we should analyze the concepts or realize the concepts what you have learned. What is mean by the stress induced rate or the rate of deformation occurred while it is subjected to different kinds of loads. Okay. So you can come along with me by writing some important formulae before we commence with the problems. First one is the stress are direct stresses or normal stresses. Okay, is given by sigma, whether it is tensile or compressive. Okay, depends on the direction of the load acting. Okay, so this is given by sigma t or sigma c. So which is equal to P by A. So where in this is stress is expressed in Newton per meter square. So where this P is load acting or external load in newtons, and area is A is the cross sectional area of the member. So in meter. The second one is we'll go to the shear stresses. So sigma S, or we can write as in tau. Shear stresses are denoted by. So shear resistance by shear area. So this is P by pi. Okay. So next we have an proportionality constant or moduli of material for this direct stresses, that is modulus of elasticity or elastic constant. According to Hooke's law, E is equal to stress by time. So this ratio is constant, so within elastic limit. So another important formula. So whenever a material undergoes tensile or compressive, so it will subject to some deformation. So that deformation are in terms of elongation. or whether it is increase in length or decrease in length. So this delta L can be calculated by this mathematical expression, which is PL by AE, where so we know that P is load applied, Newton. So this is in millimeters or meters. So shear stress also expressed in Newton per meter square. And L is length of member or body, and A is the area of cross section or cross sectional area square, and E is the Young's modulus or elastic constant, which is in Newton per meter square. So these are the some important expressions we have come across in dealing with problems related to direct stresses. So next, we're going to see some conversions and units. So we use are in dealing the problems. So let's take this part. This parameter. So unit and conversion. The first is we use length. So in meters, in SI units, okay. So we know that 1 meter is equal to 10 power 3 times millimeters. And then, so on symbol is small l or capital L. We'll use next diameter. So small d. So this is also in meter. The same 1 meter is equal to 10 power 3 times millimeter. When we come to the area, so A, so this is in meter square, or 1 meter square is 10 power 3 times millimeters, sorry, 10 power 6 times millimeter square. So then we go to the load P. So in Newton, here 1 kilonewton equal to 10 power 3 times Newton. So when meganewton is equal to 10 power 6 times Newton, we use it in conversions. The fifth one is the stress, sigma, the direct stress, tensile and compressive. So this is in Newton per meter square, or called as Pascal. Pascal is equal to 1 Newton per meter square. This is an important conversion. So 1 Pascal is equal to 1 Newton per square. 1 kilopascal or 1 kilopascal is equal to 10 power 3 times Pascal, or 10 power 3 times Newton per meter square. Similarly, megapascal is equal to so 10 times 10 to the power of 6 times Pascal, okay, or 10 to the power of 6 times Newton per meter. So you are say 10 power 6. When we convert this meter square, it is equal to millimeter square. When we take out Newton into 10 power, so meter square is equal to we have 10 power 6. Okay, so mm square. 1 meter square is equal to 10 power 6 millimeter square. So these two will get cancelled. So it forms Newton per mm square. That means 1 megapascal is equal to 1 Newton per mm square. That side. Okay. So similar way, so 1 gigapascal is equal to 10 power 9 times of Pascal, or so 10 power 3 into 1 Newton per millimeter. So these are the important conversions. This plays an important role in solving the problems without any mistakes. And one important suggestion is when you express the units, so it has to be in same either in meter square, either in millimeter square. So for example, if the Young's modulus is given in Newton per millimeter square, so the area you have to calculate, the length you have to substitute should be in millimeter or millimeter square, and the stress, the value you can substitute in the expression should be in Newton per millimeter square. So all the parameters we use, we have to use it in the same system. Okay, either in Newton or in Newton per meter square. So either in Newton millimeter or Newton per millimeter square. So next we'll take one simple problem like on direct stresses. Okay, this is very simple problem. So you have to solve when you are understood the concepts well. Just have a look at the data they have given. A circular rod of diameter 16 mm, so and 500 millimeter long, is subjected to a tensile force of 40 kilonewton. So here we have to write other two terms like elongation. I've written already here. So is equal to delta L is equal to PL by AE. So this is in millimeters, or will convert into meters, and then Young's modulus E is equal to Young's modulus or elastic constant. So this is also in Newton per meter square. So the same conversions like stress. So Newton per meter square or 1 megapascal is equal to 10 power 6 Newton per meter square or 1 Newton per millimeter square. We can use it. Okay. So let's take a look on this particular data they have given in finding the direct stresses. A circular rod of diameter 16 mm and 500 mm long is subjected to a tensile force of 40 kilonewton. The modulus of elasticity for steel may be taken as 200 kilonewton per millimeter square. So find the stress, strain, and elongation of the bar due to applied loads. So in solving the problems, we have to approach in different ways. Like first, we have to read the data carefully without any mistakes. We have to collect the data, what are the details they have given. And then the second thing, we have to identify what is our task, what we have to determine exactly. Then we can use the methodology. So which formula suits the given data in finding the unknown value or the finding the target or task. Okay. So in this particular problem, we can say this. We can take a simple sketch based on the data we have given. So this is one steel bar we have. It has to be there for solving the problem. You can understand well. See this one circular rod. Okay. To take this one rod. So this of having a diameter of 16 mm. So diameter 16 mm and a length of 500 millimeters. Okay. So next, what they have given? They have given the type of force is tensile force. So here they have given the material also. First we'll write this, the type of force. So say this is an axis of this rod. So the tensile force acting will act towards the, away from the body. Sorry, the tensile force will act away from the body. They have given the magnitude. This is in line with the axis, and the direction of the force is away from the body. So they have not given any boundary conditions, whether it is fixed or one side or not, like that. Okay, we can apply the tensile force on both the sides. Okay, so the direction is moving away. So they have given the magnitude P is equal to 14 kilonewton. And then the type of material the steel rod is made of. We have mentioned that it is the material used is steel. Okay, this is also important. And then it is having an elastic constant E is equal to 200 kilonewton per millimeter square. So this is the one simple imagination we can have, or we can just sort it out by by knowing the given data. Okay, let's find out which is the most suitable formula for finding the stress and strain and elongation. So we have this data like load is there of 40 kilonewton. We'll convert that into newtons, 40 into 10 power 3 times newton. And then Young's modulus they have given. Okay, so from kilo to newton per millimeter square, you can convert. 200 kilonewton per millimeter square is there. So 200 into 10 power 3 times newton per millimeter square. So L they have given length of 500 millimeter itself. So we'll plot that. Then diameter of the rod D is equal to 16 mm. So everything is in millimeters, both dia and length. So you have to look out this Young's modulus. This is in kilonewton per millimeter square. That means you have to express the length and the diameter and area should be millimeter square. Either you can convert this to newton per meter square, like that. So it has to be expressed in same way. So first what we have to do, so in finding the stress or determining the stress, by using this diameter of the rod, we can calculate this area. So area of the rod is given by 5 by 4 times d square, right? So 5 by 4 times diameter is 60 square. So it will give you the area of cross section of the member which is resisting the load. So that is given, it has 201.06. The diameter is in millimeter, so the area is in millimeter square. Okay. So next, look at the formulas. Okay. So how means we can find out the stress? We have the load and we have the value of area. Then simply we can use the stress is equal to P by A. So here the stress or induced stress, whether it is because the load acting is the tensile load, the stress induced to this action are the stresses which is opposing this action is tensile stresses in this case. Okay, the types of stresses induced are tensile in nature, which is given by P by A. So you can substitute the value of P. They have given the 40 kilonewton and the area of cross section, so 201.06. So thereby we'll get an value of induced stress 198.94 Newton per millimeter square. So this is the area we got here, and then by substituting the value of load P, this is, and area of 201.06, will get an intensity of stress induced due to this action of 40 kilonewton across an area of cross section of 201.06 millimeter square. The value of stress induced is 198.94 Newton per millimeter square. That one you have to realize. So from the basics, fundamentals or understandings what you have learned from the beginning of the class. So next, we have to determine the strain also. So we know the formula of Hooke's law. So the stress is directly proportional to strain. That is, the stress by strain is equal to elastic constant. So by rearranging that, right? So this formula. So according to Hooke's law, modulus of material is equal to stress by pride. Okay, so we have a stress value and we have a elastic moduli value. The only one parameter is left unknown, so we can reuse this or rewrite this formula into strain. So in this case, the tensile strength due to the action of tensile loads given by sigma by E, the ratio of stress to elastic modulus. So substitute these values in this particular expression. So stress we got around 198.94 Newton per millimeter square, and we have an Young's modulus of given 200 into 10 power 3 times Newton per millimeter square. So here many of the students will make in substituting the parameters in terms of units. So here the load should be in, the stress should be in Newton per millimeter square, and the value of elasticity also in Newton per millimeter square. You have to concentrate bit while substituting the values. So we will get a strain rate of around 0.000947. Okay. So due to this action of 40 kilonewton across the area of 201.06 millimeter square, so there will be an intensity of induced stress of 198.94 Newton per millimeter square. Due to these actions, it will undergo a strain rate of 0.00947. Okay. The next parameter we have to calculate is the elongation. So it is given by the direct formula PL by AE. So we know all the values. Okay. So P the load we know, and L is the length of the rod, and A is the area of the cross section, is the Young's modulus. Substituting all these values, we can get 0.497 times a millimeter of elongation. That means, so the member will undergoes the change in length. Okay. So due to this action of tensile loads, so this change in length or elongation it is occurred in this condition is 0.497. Okay. So we can calculate by other means also the value of this elongation. So we know that in a simple way. So the ratio of the strain, definition of strain is given by the change in length to virginal length. Okay, we can use this expression also. So we have to calculate this change in length or elongation. So we have the strain value and we have the virginal length of a rod. So by rewriting this, the change in length or elongation is given by strain into length. The strain induced we got here 0.000947 into length of the rod is 500 millimeters. So this will give you the same answer like elongation what we got from the using formula PL by AE, that is it is I think 497 times millimeter. Same. So both the methods are same. You can use the simplest one which you feel better. I hope you understand this particular problem, and you can solve these kind of problems based on direct stresses. Okay, so that means you have to realize here. So for inducing the value of stress of 198.94 Newton per millimeter square, so it is requiring a load of 40 kilonewton. It has acting on 201.06 times of millimeter square area with a material of steel and having an Young's modulus of 200 into 10 power 3 times Newton per millimeter square. For these conditions, okay, for this applied load and for this given modulus of elasticity, so acting on this particular cross-sectional area, so we'll get a value of this intensity of stress. So thereby we can decide, so for which magnitude of load, what is the rate of stress induced, and what is the deformation it is occurred due to this induced stress and due to this action load, whether it is in safe margin or not, and what is the maximum load it can withstand, okay, and what is the failure load which affects the failure of a structure or member. So you can estimate all these things by dealing the aspects like this. Okay. So next we'll go to the another problem. Okay, I'll conclude it. So in one simple problem similar to this previous one. So this is in terms of compressive load. Okay. Here we have one steel column is around 120 millimeter in dia and 3 meters long. So you have to find the intensity of stress and the strain when it carries an axial compressive load of 950 kilonewton. So take the Young's modulus or modulus of elasticity is equal to 2 into 10 raised to 5 Newton per millimeter square. So from this data, so first we have to collect the whatever the given details. So they have given the diameter of 120 millimeter and length of 3 meters will convert to millimeters. Then Young's modulus they have given it as in Newton per millimeter square only. Then applying external load and compressive type of load of 950 kilonewton. So first by using this diameter, we will calculate an area of the cross section of the steel column. Okay. So write a simple sketch for this condition also. This one steel column is there, so take out. Okay, made up of steel material, right? So this is having an 120 meter dia. And length of 3 meters, that is 3 into 10 power 3 times millimeters. And this is applied by an compressive load of 950 kilonewton. So this steel column is subjected to an compressive load. See, the direction is towards the body. Okay. So this is of magnitude they have given 950 kilonewton, which is equal to 950 into 10 power 3 times Newton, and the elastic constant is equal to 2 into 10 raised to 5 Newton per millimeter square. So this is the nature of the problem, the conditions they have given. So for this, the first we have to calculate the area of cross section which is resisting this particular load. That is given by, so area is 5 by 4 times diameter square. So 5 by 4 into diameter is 120. We'll substitute the values. We'll get the area of 11,309.76 millimeters square. So then, after the area, by using the load applied and the area of cross section, we can calculate the compressive stress induced in steel column due to this action of 950 kilonewton. Then we can determine easily the rate of intensity of strain, that is by dividing stress by Young's modulus. Both are given in the problem. So thereby we can evaluate or estimate the rate of stresses, compressive stresses induced due to the action of compressive loads. Okay, and the intensity of strain in this particular case. Okay, I hope it's clear now the concept of stress and basic types of direct stresses and indirect. What is the mean by the indirect stresses? And what is the nature of tensile, compressive, and shear stresses? And then we talked about elasticity, plasticity, and elastic constant concepts. Okay, and then we have seen the Hooke's law and demonstration by means of one experimental setup in the today's class. Okay, so I hope you all understood these concepts well, and you can ask your questions at the end of this session. And thanks for your attention.